Okay, Assalamualaikum dan selamat pagi. Okay, today we will continue on the analysis of heat exchanger, slide number 13 and so on. Okay, basically when we like to analyze an heat exchanger, there are two types of way to analyze it. The first one is we call it LMTD methods or lot temperature difference methods, and the other one is we call it an effectiveness NTU methods. So there are two way lah. So basically what you need to know by having these all methods. First thing is these are the formula of it. So here we have for example, here we have a Q equal to MC CP CT C out minus CC in and so ever, and then we have here one H. So what is it all about? So the first one we have to know what is this stand for. M dot is mass flow rates for the cold sites, and MH is mass flow rate for the hot sites. CPC is specific heat, C for the cold sites, CP H is for the hot site. Okay, and we have here TC out and TH out. This is outlet temperature for the out. So you need to know either which one is TC out and TC in. For example, here we have this. We have to know by seeing at this flow. This is a hot side because it's in hot color, and the temperature is a bit more than compared to the other one. Perhaps this one is, I don't know, 80 degrees Celsius, perhaps 80 degrees Celsius, and this one maybe 100 degrees Celsius. So this is TH in. Okay, so we have here is TH out. Okay, here we have because the cold side is on the other way. So we have here, this is TC in. Here is the value for the TC out. Okay. So here you need to determine which one is out, which one is in. So by knowing this one, you could easily solve whatever equation that you need to solve. So basically, all the formula will be given. So here we have Q dot equal to TCC times TC out minus TC in. So this is one way to know what the value of Q. The Q is the same if we compare this Q over here. Q over here is equal to Q over here. So you could use by TCC. This is heat capacity rates for cold. Calculate by using this formula M dot C times CP, or you could calculate CH equal to M dot H times CPH, and this is Q. To calculate by using this one, and this is to calculate the total Q by using TLMTD method, which is U times E times delta Tm. This is average appropriate mean temperature difference between the two fluids. Okay, let's see the detail of it. Right. So okay, this is arithmetic mean temperature difference. This is T that you need to calculate. Okay, you just go directly to the formulas. Okay, this is TLMTD. If you want to calculate using these formulas, so Q dot is equal to UA S delta T LMTD. So U is overall temperature coefficients, and have here AS is area, surface area, and we have TLMTD. So what is TLMTD? TLMTD is delta T minus delta T2 over ln delta T1 over delta T2. So what is delta T1? What is delta T2? So basically, when you look here, this is parallel flow. What do you mean by parallel flow? Because this is cold water, it's moving that way. This is hot water, it's also moving that way. So this is parallel, parallel flow. And here we have a delta T2. Delta T2. Okay. It's either, it should be positive lah. Okay. Delta T2. What is the difference? Because we need to minus it. So TH out minus TC out, and you have a positive value. Because this is out is supposed to be higher than TC out. So minus this one, TH out minus TC out, and you have delta T2. And this one, if you look over here, this is delta T1. So which one is highest? Minus the lower value to have a positive one. So TH in minus TC in, you have a delta T1. So this is a complete formulas. Okay. So let's have a look on the difference counter flow. What's what we call by counter flow? Counter flow is different flow direction between the cold and the hot fluids. Okay? So over here you see the cold fluids moving here, going there, and going here. So inside this whatever shell, so we have inner tubes. This inner tube we have a hot fluid. Maybe this one is water, maybe this one is refrigerants, right? So this one is counter flow. Then over here we have a TC in and we have TH out. So here this is delta T2, okay, delta T2. So H out minus TC in, we have a delta T2. Okay, why this is delta T2 not delta T1? Okay, because of course we will like to reduce whatever the temperature of the aim of this heat exchanger is to reduce the temperature. So it's supposed to be the focus on the hot fluid. Okay, so when this is hot in, this one, this is hot out, this is 2. So delta T2 is TH out minus TC in. And we have another one is delta T1. Delta T1 is here is supposed to be TH1, TH in minus TC out. Okay? So this is the complete formulas. Okay? Having these two formulas, you could easily calculate delta TLMTD, and then you could calculate Q. Okay? Sometimes Q is already been given. You need to calculate U. So rearrange these formulas. Okay? Q given, calculate U. Rearrange this formula, then you could calculate U. Sometimes you need to calculate E. So by rearrange this formula, you could calculate, bring everything over there, you calculate ES, because this has already been given. Okay, ES from E, area is dependent whatever that you have. For example, if you have area is equal to pi r squared, then you will calculate r, because you already have the formulas. 2 pi rl, then you calculate l by having if this is A. So let's see later on what we have. Yeah. Okay. The next slide. TLMTD is very suitable in determining size of heat exchanger to realize prescribed outlet temperatures find the mass flow rates, and the inlet and the outlet temperature of the hot water are specified. Okay? With TLMTD methods, the task to select heat exchanger that meets the prescribed heat exchanger requirements. The procedures to be followed as below. Okay? This is a way to select an heat exchanger. Select the type of heat exchanger that's suitable for the application. So this one you need to know what is the types. Maybe this is maybe okay, maybe this is counter flow. Okay, because counter flow is better compared to the parallel flow. And then what you need, maybe shell in tube type, shell in tube type. Okay, or you need a very compact space, then you need to change to plate type. Okay, plate type is just exchanger, because plate type is very compact compared to shell in tube. It is too big, it needs a very spacey, you need a very large space. And then number 2, determine any unknowns inlet and outlet temperature and heat exchanger and heat transfer rate using energy balance. So energy balance, this is E in equal to E out. So having these formulas, actually this one is Q lah. Q is equal to E in, and we have another one, Q equal to E out. So we have Q equal to MC delta T. Q equal to, what's the formulas? I'll go back on the previous slide. We'll work to the second chapter. Q equal to KA delta T. KA delta T over L. So we have E in and then next E out, equivalent or not. Then you have temperatures in and temperatures out. And then calculate the log mean temperature difference and correction factor if necessary. So normally they don't have a correction factor lah. Okay? So calculate TLMTD as before, then obtain or select, calculate the overall heat transfer coefficient. So but because it's already know Q's you got from here, so Q equal to U ES delta T delta TLMTD. So you need to U equal to U over ES delta T LMTD. Okay. And then calculate the area of surface if needed. So area of surface E equal to Q over to U ES delta T LMTD. Then you have A equal to 2 pi RL, and then bring everything over there, then you can calculate L needed. Okay, let's have a look on this exercise given. Okay, and overall heat transfer coefficients. So I need to erase. Sorry. Later on I erase it by not saving it. Alright. The next one is okay. The next one is solving using LMTD method. So this is okay. Here you have a heat exchanger. This flow, water flow is over there. This is the flow. So you need to calculate TLMTD. Okay. T1, this is T2, yeah, this one is theta T1, okay? And you have everything, but you don't have this one, select TC out. Okay, here given the heat transfer coefficient exchange is W meter square Kelvin. This is U. So specific heat of the water is equal to Cp to the 4.18 kilojoule per kg. Determine the length. So you need to find the L. Okay, to find the L. So this is formula how to find it. Okay? The first one, find the heat transfer rate of waters. Okay? Heat transfer rate of waters. This one is MC delta T. That's what I said before, because of this the water, we need to know how much energy for the such of water have. So Q equal to MC MCP delta T. So here we have 1.2 kilogram per second, amps, see whether or not. Here is the mass flow rate, 1.2 kilogram per second, and then we have Cp. This is 4.18 kilojoule kilogram Kelvin, and we have a T out minus T in. This is the T out minus T in for the cold waters. Okay? So we have this is equal to 301 kilowatts. Okay. And then we need to find the temperature outlet at second temperatures by having the same formula, because Q is the same for everything. If you have a look on this, so Q is the same. Whatever that cold water had absorbed is equal to whatever that been released by the hot waters. So here, whatever that supposed to be hot water is transferring the Q is equal to Q is going there. Only some will be minus, some will be positive. So Q is the same. Okay. So here we're using that these formulas. Okay, because it's involved fluids. Q equal to MCP delta T. Then here we have for the hot water side. Then rearrange this formula because we don't have T in. We rearrange these formulas. We don't have T out. So rearrange the formula given, and we have T in minus Q over MCP, because Q is the same, because it's being transferred. Heat is being transferred, is the same. So we have here Q equal to MCP delta T. Here the minus the positive sign being ignored, because it's equal. This is E in equal to E out. This is energy balance actually. So whatever Q is the same. So and then we have 160 minus 300 K over 2 kilograms per second. given or not, 2 kilogram per second. Alright, this one is 2 kilogram per second, and then over 4.31. It's not been given here. Perhaps it's in the tables. In the tables, we need to find this whatever here inside the table, CP for the Giotto mode. So we have Q out is equal to 1 to 5. Okay. So we already know T out equal to, for the hot water, TC out, TH out, TH out for 1 to 5. So we could easily calculate these formulas by having this TC out and TC in, and we got this 80 and 105, and we could calculate TLMTD, TLMTD, and then plug in this TLMTD inside these formulas. U is already been given. 640. So A is not been given. Q is here. It's the same Q. Okay, 300 kilowatts, 301 kilowatts. So then you got A is equal to 512. Okay, so area for the length of the heat exchanger. So this is exchanger basically is cylindrical. Okay, basically heat exchanger is cylindrical. So area of surface area of cylindrical is equal to A equal to pi R pi 2 pi R 2 pi R atau pi dl. So here you need to calculate the L, the range AS over pi d, and you have it over here 109 meters.